Right. Thanks, and it's a pleasure to be here. First, I want to start off by thanking our wonderful organizers, Tarun, who is missing, Subir, Saurabh, Mayuri, Muhammad, and Prabha. Thank you so much for having me here. I think it's my third time in Bangalore in the past year and a half, so I always feel welcome coming here. And the title of my talk that I'd given the organizers was, How Light Can Dark Matter Be? If you came here to find an answer to that question, well, anticipation. Unlike most times, I will tell you, the answer is on the board, okay? Dark matter cannot, with some caveats, I claim, cannot be lighter than 10 to the minus 19 electron volt. Okay? If that's all what you came to hear, then that's okay, you're done. I'll take questions, and we'll go to the next talk early. So, yes. We're done, yes, please. Then we will learn about why I get this bound, okay? Yeah, so we'll find it.
You're only dealing with one type of dark matter.
That is also something that will come up. Those are all caveats that will come up. This is for a single species dark matter that makes up the entire universe. And there are even more caveats that will come up, but I think this is a pretty, as I'll try to argue, it's a reasonable number to go by. All right. Their caveats are there, and hard to read at the moment, but wait for the talk. And by the way, I should say apologies to Lyman and others. This is not the CMB, even though it looks like it, and because it's evolving, so it's not on regular timescale anyway. So it's not the CMB despite the color scheme that I've chosen. Okay. So what I want to tell you started off in work with Mehrdad over an afternoon conversation, Mehrdad Mirbabai, over an afternoon conversation when I was lecturing at ICTP, where Asim was also there at that time. And we sort of came up with this bound. But really, the talk I want to give you is not just about this bound, but about all the fun we have had since. In trying to think about this bound, we realized we had to think about this idea of warmth and randomness in waves. Okay? And that really got me quite excited and interested. And as you can see, like with a bunch of collaborators, we've been having a lot of fun over the past, since the first paper. So I'll tell you a little bit about this. I, of course, won't be able to tell you everything, but you can ask me afterwards. And my collaborators, Mehrdad Mirbabai is ICTP Trieste, Xiang Ling, who was a graduate student at Rice, and he is now in Hong Kong, Sen Delos, who is a postdoctoral fellow at Caltech and Carnegie Observatories, Zimon Mai, who was until recently at Perimeter, but now has just moved to Germany, and Kelly Yang, who is a student at Rice University, where I'm at as well. Okay. So, dark matter exists. We don't know what it is. Okay. We know about the existence of dark matter through its, of course, I was being glib when I said it exists. I mean, this is still, we should question, but for this talk, it exists. We know about dark matter from its gravitational interactions. So at the very minimum, and we also know that it must be gravitating, so it must be reasonably non-relativistic, which means it must have a mass. So at the very minimum, we think if dark matter is made up of particles, especially fundamental particles, the particles must have some mass. We don't know what it is. If it is made of fundamental particles, it must also have a spin. Again, we don't know what it is. It may also have charge and interactions, but these are not necessary. So I will focus on these two things first. So in this spin versus mass plane, The vertical axis is dark matter could be bosons or fermions. Yes?
You say interactions are not necessary, I just mean strong interactions, as in strong enough to be detected.
Yeah.
Some interactions have
You,
to be there.
you could just have, gravitationally, you could produce dark matter.
Gravitationally.
You could produce it. You can have very small Planck scale interactions. Not so much, but I'm happy to answer questions. But you can produce it gravitationally in the early universe. It's not necessary. To have Planck scale interactions are enough to do these things. So you don't need it. So it could be bosons or fermions. That's the vertical axis. Or it could, and the mass, as you all know, embarrassingly can have a very large range. And Glenn will say you should go much far beyond this as well, because it could be composite as well. I'll focus on fundamental, what I think of as fundamental fields at the moment. But not all, why do I think of spin and mass together? Because it gives us information. For example, as you all almost certainly know, if I assume that dark matter is fermions, it immediately cuts out a large range of this parameter space. Pauli exclusion will tell me that dark matter cannot be lighter than about 100 eV. This has been known for decades. You can't fit in if you make them too light, you can't fit in enough of them to get the correct density because of Pauli exclusion. On the other hand, this region that was cut off, if it was fermions, again gets opened up if we start thinking about bosons. Bosons, again, could be spin 0, spin 1, spin 2. Again, I understand the theoretical difficulties with spin 2, but for the moment, let's keep them. Once you become much lighter than an EV, what happens is that the de Broglie wavelengths of these particles overlap significantly for a given density. And they overlap so significantly, it sort of stops making too much sense to think about them as individual particles. And they merge together, and you can think of this as starting to behave like a mean field or a classical field. Okay? So in this regime, when you get sufficiently light, which is allowed if there are bosons, the occupation numbers become high, and you start treating this as a classical field with some asterisks here. And if you are thinking of the lightest mass, you end up thinking about this regime. So that's the regime we are going to focus on. So by this last slide that I just showed you, the fact that they overlap and it starts behaving like a classical field, in recent years, this has started being called wave dark matter. So that explains one of the words in my title, this wave part, right? Because it starts behaving like a classical field. But what I really want to tell you about is this new part about warmth and randomness, okay? And how does it affect that bound that I talked about. So when we think about fields or waves, we have to, the first thing, and we are doing cosmology, so I have to think about initial conditions. And this breaks up into two types of initial conditions. Here, imagine you have a large region of the universe. This is the Hubble scale roughly at that time. This is one example of an initial condition for this wave or field. It's got an almost homogeneous value throughout space. Okay? Slight fluctuations, but you can't see it on this scale. Another possibility is that the initial conditions during radiation domination on this horizon scale is quite bubbly. Okay? It's fluctuating a lot. When I refer to cold versus warm, okay, as you will see, I'm referring to this as being cold and this as having the possibility of being warm, even though these are waves. I'm not talking about particles here. Just a little bit more detail. So this is just a one-dimensional slice of what I had shown you before. So the vertical axis is a field amplitude. Let's take it to be a scalar for simplicity. The horizontal axis is space. Here is a horizon scale. This is a field that's homogeneous on multiple horizon scales. This is a kind of field that you get, for example, for an axion with PQ transition that isn't broken after inflation. So it would be homogeneous. This is globally misaligned during inflation, for example. Another example, the warm aspect of this would be if you had a field that was varying rapidly on horizon scales. If it is varying rapidly, let me imagine there is some length scale, k star inverse, a co-moving length scale like this, over which there is some coherence or some correlation, beyond which the correlation disappears. This scale, a length scale, would be k star inverse, so k star is like a momentum scale or a wave number. I can take this k star and the mass of the field, and I can construct a velocity out of it. So momentum over mass, I can construct a velocity. So if this number is not too small, then I can think of this as warm. Notice k star in this upper part is essentially 0. So the velocity is 0, hence the upper one is cold, this one is somewhat warm. Let me, throughout the talk, we'll focus on just these two numbers, k star and m, and k star over m, or any, yes, please.
So by warm, I think you really mean this pressure flow, or some amount of pressure, rather than actual some sort of equilibrium.
Yes, I am not talking about a, yes,
Yeah.
right. So there's some, what I mean by that is some significant velocity dispersion, okay? That is observationally relevant.
Doesn't the axion random walk during inflation if the mass is less than the Hubble parameter?
It does, but it still creates a almost, the end result is that you, the dominant mode is still long wavelength.
Yeah.
So if you ask what is the typical momentum, it's still going to be very small in the system. Okay. Why do I want to think about this system? Because A, as I'll argue later on, this is not so unusual to have in many models, but more importantly, perhaps, I claim that thinking about these systems like this immediately allows you to think of some observational consequences that might be accessible. Okay. So let's think about what this happens, okay? So suppose you have a field in the early universe that's dominated by sub-Hubble field modes. Then I claim that if you look at the density fluctuations in the universe today, it will leave some features. On the vertical axis is the dimensionless density power spectrum, so P of delta multiplied by k cubed. Horizontal axis is the co-moving wave number. To just orient you, the dotted line that I'm showing here is just the lambda CDM value. Okay, this is just the log of k squared part of this at matte radiation equality. And the upper dotted line is how it evolves if you, during matter domination, how high it gets roughly. However, if you have a field like this for a correct appropriate pairs of parameters, you will find that it will deviate from this lambda CDM prediction. How will it deviate? First of all, the fact that there is a finite coherence or correlation length will mean that you will end up with some white noise or uncorrelated region, which is what corresponds to this k cubed part here. The fact that there was some velocity in the system, meaning the particles or the waves were wanting to move around, they will move around to some distance, wipe out structure, and that will give rise to a free streaming type suppression in the system. As the system evolves, you will find that some of these features are maintained and new features such as the gene scale also emerge in the system. So you introduce features away from CDM because of just this idea that the field has variations. Okay? Yes? Oh, which one? This one? There is no departure. It's just a way of, which one here?
You see the dotted line does not quite match with the solid line. The
Which one?
darker solid line.
I've drawn this in Keynote. Like this is like a, yeah. This one? This is equality. This is K equality. So in the Newtonian gauge, the K, this would have been flat outside, right? So that's why it's K equality is here. Right. The faint dotted line is lambda CDM.
CDM.
CDM, sorry. Yeah,
Lambda is
lambda is there's no effect here. So CDM, okay, it's just CDM. At this point, lambda has done nothing to you. Okay, so this is just CDM. Okay. So my claim is that these features, because they arise, it's worthwhile thinking about this, and these can be, okay, if you're in the business of putting bounds. This will allow you to put bounds, but hopefully, by knowing these features exist, we can actually detect this. So, as I will argue, the fact that these features have not been seen in the data will give us this bound that I referred to, and I will get to that. Of course, this also gives motivation to search for these features in the data. Yes?
So normally, when we try to relate to observables, we sort of construct smooth density fields, right? And so normally if you have like features, they tend to get washed out by that scale. And here I see a white noise curve that just sort of keeps going. And what I think about white noise, I think about something that's actually temporally varying as well, right? So you're saying this is something that survives this into the smooth density field?
Yes.
Okay.
Absolutely, it does. Right. So there will be a scale below which it will not enter, and there'll be a gene scale basically, where it's moving too fast, below which things will not cluster. The gene scale is here. So this stuff looks like delta rho of order unity, but it's not really, that's just your discreteness, right? That has nothing to do with clustering. The gene scale is, of course, as always, what you care about, because there things are not moving so fast that you don't actually cluster. But good point, okay. But yeah, this part is the smoothed part, right? So it's not just discrete. Okay. Something that's also exciting about these models, or this way of thinking about it, is that this enhanced structure that you see here leads, when you think in the nonlinear regime, it will give rise to early growth of structure. To just, give you a little bit of number to keep in mind, at the bound that I'm going to be talking about, you get halos and solitons forming. Solitons are these dense objects at the center of the halos that form, even at a redshift greater than 100 in this case. Okay, so it's very quick formation. I'm not saying stars or galaxies, just dark matter at the moment. So this is also exciting that these things also make these predictions. So, and if I have time, I'll show you that structure formation looks somewhat different in this case. Okay, let me skip this for the moment, and then I'll come back. Okay. So I've given you already told you what the punchline is, right? That thinking about this, you can get a bound on mass, and the phenomenology is interesting to think about it. And I'll also, as time permits, I will tell you a little bit about how to do the calculation, which has this research that has excited me a lot over the past year, at least. But here's the way I'm organizing my talk. I'll give you a little bit more about what models are available that create this type of a field. I'll spend most of my time telling you then, how do you get these features in the spectrum? Okay, what is the physics from there? I'll tell you a little bit about the analytic techniques that we have developed to calculate some of these things, then the bound that I mentioned, and likely I will run out of time to talk about simulations, but we'll see how we get there. Okay, so I said, imagine you have a field that looks like this in the early universe. One of the key features here compared to a globally misaligned one is that this has no zero mode of the field. Okay, if you average this field, it's zero. So is this a common thing to happen? Of course, we don't know how nature works, but we can look at many models that have been put forward about the early universe production of dark matter. And is this something that arises quite generically? And my answer to this is yes. Okay. For example, if you think about the QCD axion with a phase transition, QCD phase transition after inflation, it will give rise to this kind of a field configuration. If you think of converting energy stored in some homogeneous mode, and that converts energy to a field that is going to become your dark matter, it will almost always give rise to this kind of a field configuration. If you try to generate these fields from topological defects or non-topological defects, again, it will give rise to this. Part of this is, why is this always happening? It's, roughly speaking, it's just causality. You're not going to correlate the field values over distances larger than the horizon scale, so you're going to have variations. So that's why.
Topological defects decay into axions, they will create highly relativistic.
They do, but they will still be, if you look at the field configuration, it will not be homogeneous.
No.
It will have these features in there. So I completely agree with you. The topological defects will create things which are relativistic, but if you look in field space, that just means fast varying space. It's inhomogeneous, right? The field is highly inhomogeneous. Yes? Sorry? the density will have a zero mode because the density is square of the field. So if you take the average, it'll still be a homogeneous mode of the density. The field doesn't have a homogeneous mode. If you average the field, the field value is, the average of the field is zero. The average of the density is non-zero because, as you know, density is field squared. Right? So you get a zero mode of the field, no zero mode of the field, but still a zero mode of the density. Okay. So it's causality that should give you this. Of course, the one thing that escapes this is if you produce these fields as Subir does during inflation with the stochastic way of producing that, that Dick can tell us a lot more about of how these fields get misaligned. You can do that for light scalar fields. That's another option, and that's a popular one. So that escapes what I'm going to say. However, if you even try to produce a vector field during inflation, you will still get this as the field configuration at the end of the day. You can't get it to be homogeneous. Okay? So again, this is just me being somewhat of a salesman right now to just tell you that this is something to at least pay attention to. There are many models here that will give rise to something like this. This is in position space, which is easy to visualize. But if you look at this in Fourier space, the power spectrum, which means Q cubed, times the field spectrum will look like it's peaked. There'll be some characteristic scale, which is just what you see in the position space picture. If you wait long enough, because this field better have mass, it will become non-relativistic because momentums will redshift. If you wait long enough, the peak will also become subhorizon. Okay, so both of these things will just happen because the universe expands. So this is a very generic thing you should expect to have at some point. Okay, so this is the field spectrum, and these are the models that are available that would generate this. So what should we, now let's go to how does this translate into densities, and how do you get the features that I described? Here is the field spectrum. What does this do to the density fluctuations? At early times, meaning during radiation domination, I claim that you take this field spectrum and include the fact that inflation potentially has set up the adiabatic fluctuations in the early universe, you will find that the density spectrum will have an adiabatic piece that looks like this, and then on short scales, it will have this bump. So Glenn, maybe this answers your question, that the density fluctuations still have the usual part on large wavelengths. On short wavelengths, you will have extra power because of this fluctuations. So the momentum at which this power spectrum was peaked, it's the same thing roughly that this comes. Yeah, it's the same. So K white noise is roughly just the same scale, up to order unity factors. So let's try to understand. Sorry? So the power spectrum is correct, but its contribution, rho bar times delta, will of course be small during radiation bar. This power spectrum is correct as it is, but of course this is power spectrum of the dark matter alone. Okay? So this is just power spectrum of the dark matter, okay? Not of the total matter. Okay, so let me just try to explain where this, the adiabatic part, perhaps most of you are already familiar with. Let me explain this K cube part. Again, for the experts, this will be obvious, but let me do it anyway. Here's the field spectrum. You want to constrain a density spectrum, it will turn out to be a convolution over two field spectra, because density is square of the field. There should have been a convolution, a Q and a K here, but as long as you ask questions which are on scales small compared to the peak, that K drops out, and this whole integral just becomes a constant. So is there a chalk? Yeah, okay. Thank you. So density is field squared. So P of delta will go as an integral over P of phi Q, P of phi Q minus K. This is what the density spectrum looks like. As long as you ask the question on K much less than that characteristic peak in the spectrum, this is roughly constant, and that's exactly white noise. Right? So there's nothing much going on. It's there. And if you multiply this by K cubed, you precisely get this K cubed part. Another physical way of thinking about this is there's a lack of the two-point correlation function in position space vanishes beyond some region. The Fourier transform of that will be constant, so that gives you the Poisson or white noise spectrum. Okay, so it's very, there's not much going on. It doesn't really depend on the shape of the spectrum in detail. So that explains this K-cube tail, K-cube part. And it will have a cutoff because the power doesn't go on forever in this case. Okay. Now the next two slides are perhaps more interesting ones. So here is what you started with during radiation domination. The visual representation of this is from a full 3+1 dimensional field simulation. You notice there are two scales here. One is a long wavelength scale, which is the adiabatic part. This is a long wavelength mode. The short scale stuff is this isocurvature bubbliness that was there in here. So this part is, the blue part is extracted from here. The orange part is extracted from here. Let's see how the system evolves in radiation domination. All the fields are doing are trying to move around. They have velocity, they're just trying to move around. And you can try to take a moment to guess what's going to happen to the system in radiation domination. And first look at the bottom part. It does hopefully what you expected, that these fields move around and they erase this inhomogeneity in the long wavelength mode. So notice that you've just gotten rid of this because free streaming just erased the inhomogeneity. At this level, okay, so this is what you're left with. Look at the power spectrum now. Notice that I have only erased the adiabatic part of the power spectrum, but I've left this isocurvature part as it is. It might seem counterintuitive, but think about if you were to take the power spectrum of this field, this feature would never go away. It's still there. This part goes away because that was the correlated part of the spectrum. Another simple way of saying this is white noise in this case is uncorrelated. What are you going to do with uncorrelated stuff? You can't remove more correlations. It's going to remain as it is. There are many different ways I can say this, but this is true. So you only erase the adiabatic part, and this is because of free streaming, stuff moving.
Can you decrease the amplitude of white noise?
Not in this region. Over here, you can have some evolution if the field is relativistic. But this part will not change. If they're just free fields moving around, this amplitude cannot change. If you want an intuition, which I'm now going to run out of time already, but if I have Poisson distributed point particles in this room, right, so you already know. Okay. Poisson distributed point particles in this room with random velocities. You take the power spectrum, it's white noise. Close your eyes, open it again. The particles have moved around. The power spectrum hasn't changed. Okay. So it's the same thing that's going on. Okay. What about, now this was all in radiation domination, free fields moving around. What happens if you get to matter domination? Again, the bottom panels are simulations of full 3+1 dimensional simulations of Schrodinger Poisson fields with gravity. The top part will be the power spectrum. So you start with this at the end of radiation domination, this feature introduced by free streaming. During matter domination on very large wavelengths, that is small k, everything just grows, as you might expect. This is just delta rho over rho, goes as a scale factor. However, because there was warmth in the system, you do still have a gene scale appearing. So it's not scale independent. There's still a scale dependence here at small scales. So notice I'm making a distinction between the free streaming scale and the gene scale. Free streaming is how far particles have traveled, roughly up to matter radiation equality. Genes is about what is the scale below which structure cannot grow after matter domination. Absolutely. In fact, you will see that this part, because it's white noise-like, at least on these smallest scales, there's going to be a lot of non-Gaussianity there. Okay. As you go to larger scales, as we discussed yesterday as well, of course, the non-Gaussianity is getting washed out.
Kind of particular non-Gaussianity is the square of a field?
Yeah, essentially. I mean, it's at the leading order, it's just short. It's Poisson. it's Poisson, so you can just know calculate exactly what it's going to be. But that's at the peak. As you go lower, of course, it's getting washed out in larger and larger volumes. Okay, so I've just given you a picture of, you start with a field like this. This is the density fluctuation spectrum in the early universe. Via free streaming, you erase structure in the adiabatic part. In matter domination, you grow, but the growth is somewhat scale dependent because of the fact that you have velocity in the system. For those who have worked on fuzzy dark matter, this gene scale that I'm talking about is different from the gene scale due to wave dynamics alone. This gene scale is more in the IR compared to that scale. The most IR scale in the problem is free streaming, because that's how far particles travel. Then there is a gene scale, which is just what genes would have recognized as gene scale. And then there is, of course, a wave dynamical gene scale that is more in the UV. That's actually close to the peak here. Okay, so hopefully I've convinced you that this is how the features arise. And it's there's not much physics. It's just Newtonian physics with particles moving. There's nothing else in this, or waves moving. I will not go through this, but this is something we are quite proud of, and I'm happy to discuss of how do you actually calculate this. There's no zero mode to perturb around. How do you actually calculate the field evolution in this case? And please feel free to look into this. We actually calculate the evolution of the 4-point function, which is a 2-point function in density, rather than the phase-space distribution function directly. And we're able to evolve it. Details, especially the isocurvature part, is quite non-trivial in how it comes about, but I'm going to skip all this at the moment, and you can ask me later. The part which is great about this, as far as we are concerned, is that the same framework can be applied to particles and fields. Arbitrary fractions of each you can use. Some of it connects directly to what some of you might be familiar with, the BBGKY hierarchy. It's a truncated version of that in some limits. And we're able to solve the system. Instead of differential equations, you solve Volterra equations. You can get the power spectrum for all of these things within less than a second. Okay, so it's fast by now. Okay. If you're seeking intuition, I'm almost running out of time. If you're seeking intuition, here's just point particles with some correlated long wavelength perturbation. That long wavelength stuff gets erased. During radiation domination, you just have this distribution. Matter domination, you start clustering. So you could do this without waves also, and we have. So how light can dark matter particles be? That's how I started the talk. I claim that these are the kind of generic features that appear when you think of dark matter produced after inflation. Now you just say, well, what we did, not what you should do. What we just said is, we believe CDM, let's say up to 10 megaparsec inverse scales. Why? Say because of Lyman alpha, Lyman alpha force. Just a rough number. If you say you don't see these features, this rise or this dip, up to 10 megaparsec inverse, I claim that you can convert it into a bound on the mass of the dark matter particle. It's just the fact that we haven't observed these features. We have not used any shape information, nothing, right? So there's a lot more work that can be done to improve this. How does it compare to things existing in the literature? Apologies if your bounds are not on here. It's just a smattering of examples. The most relevant one is perhaps the one by Dalal and Kratsov. This is based on interference patterns inside ultra-faint dwarfs. It's comparable to that for very different, it's a coincidence that these are comparable. Very different physics, very different models. It's a coincidence right now. They will find a smaller system, their bounds will improve. If we can go to smaller length scales, our bounds will improve. They are not connected. Sorry?
What is your smallest? What is your observation?
Lyman alpha.
Lyman alpha.
Okay, so 10 megaparsec inverse is what the number I'm using for Lyman alpha. So that's my number that I'm using.
Mass bound scales proportionally?
Quadratically with the smallest. So mass bound will scale quadratically with the smallest scale at which you can measure the power spectrum. Okay, so it's great in that way as well. And you should ask me why this is 10 to the minus 19, whereas Tirth yesterday say it's a KeV. Right? So where is this coming from? Why the difference? Okay, if you want to look in this parameter space, and I will not do the simulation part at all, but if you want to look in this parameter space, the mass versus this K star. Okay? What I talked about gives you this wedge that is allowed. Okay? And the bound is coming from the bottom of the wedge. No enhancement gives you this line. The lack of free streaming suppression gives you this line. So you just look at the lowest value. That's where the bound is coming from. For the bounds that many other people have been using with the globally misaligned case, that is distinct from this bound, and it comes from the very low moment, meaning K star is essentially 0. It's just a coincidence that these two levels right now turn out to be the same. It's a coincidence. Measurements will change this. Okay. Okay. All right, so because I'm out of time, I'm going to skip the simulation part, but there's a lot to be said here. Even one thing I will mention is that when we calculate the mass function and look in detail, by redshift of 100, we have solitons which are forming order unity fraction of the collapsed objects in the universe. Okay, so it's pretty distinct here. Right? So I'm not saying solitons are all order unity fraction of all of dark matter, order unity of the collapsed objects. All right. Baryons are upcoming, work is ongoing, but since I'm out of time, let me end here. Thank you.
So this isocurvature peak due to the dark matter should also give rise to some gravitational waves, the induced gravitational waves on somewhat higher frequencies, right?
In principle, of course, right? Because you will, however, as you know very well, this is in delta. You need to got induced gravitational waves. You need to go to the potential, which is
Yes.
1 over k squared. This is subhorizon. You get killed by the fact that it's 1 over k squared. This is subhorizon peak. It's not on the horizon scale. Right? The peak is on subhorizon scale, so you're not going to. You will get some induced structure that's moving around in potentials, but it'll be small compared to the benefit you get when you have horizon scale homogeneities.
That's true.
Okay,
So there could still be a peak in the GW, but it might be
it will be
highly
suppressed because in radiation domination it'll be very suppressed.
Yes.
Because you're deep. But later on, sure, you can
But
generate
might-
something, but I suspect it's not.
But
a
it might be
big-
different in the matter domination because the kernel evolves differently in the matter domination compared to radiation domination.
Worth
So it
thinking about.
might- yeah.
My only concern is this is very subhorizon.
True.
That 1 over k squared should be calculated. But
Thanks.
So in the old days, which were the young days for me, we separately treated isocurvature axion from axions that were participating in the curvature. You seem to be joining them now. Why?
I think there
Do you
were.
think that there isn't the possibility of a separate isocurvature axion mode anymore?
No, I don't. I
What
think
does happen
that
is that you begin with isocurvature, and it develops by gravitational clustering into something that has a curvature aspect. And I completely agree with you, damping will occur if you have the low masses. It's actually not that dissimilar from the collision stamping of neutrinos.
yeah, absolutely.
And in fact, that's one of the reasons that the transfer function looks a
Yeah,
little bit
exactly.
similar.
Absolutely.
But the other aspect is, why does it look like white noise? Why white noise when it could, because white noise means that it's zero correlation, and there's never going to be zero correlation. So the question is, what is it that you're saying is a characteristic scale beyond which there's no correlation?
So it is absolutely true that I'm not making a claim that it will be perfectly KQ, but it will be close because just the correlation, as you know, like better than I do, the field will not be too without inflation, the field would not have been correlated beyond the horizon scale significantly. Would you agree with that? Without inflation, would you agree that there would be no correlation?
Yeah, no, the zeta is what's determining the, unless you, I mean, it's possible within axion models that arise in inflation. You can get the isocurvature mode that will have the long wavelength fluctuation. They don't. And in fact, that's what we did. That's what the isocurvature axion game was all about, which I must say, one of the more remarkable things, not much commented on, it was the very first model that we ruled out with the microwave background just because there was this huge enhancement, which we call the isocurvature effect, at actually long scales. But in your statement, it wouldn't be there.
I'm not saying it wouldn't be there. I'm saying that if that is a separate, so that is a primordial isocurvature set up by inflation. That can be small. You can't get rid of this smaller scale isocurvature. That can still be there. It can be small, depending on what you choose for Hubble and so on. That can be small. I'm saying this short wavelength one, if the PQ transition is happening after inflation, there's no way to get rid of that.
Yeah, I'm not necessarily in disagreement with you. Let me give another example, which you may or may not be near and dear to you. There was a period of a re-resurrection of what was called isocurvature baryons.
Mm-hmm. Yes.
And people were trying that all over the place. And the most natural thing was, in fact, that it would be roughly not maybe white, no, Poissonian.
Mm-hmm.
And yet, I can invoke authority, and as I said, question authority at all times. Jim Peebles decided that he could do whatever he wanted with the isocurvature baryon, and at some, I mean, there was a natural thing to say it's nearly scale invariant. That's why isocurvature axions had the constraint. And it didn't, he really didn't quite go that far, but that's the kind of game, and George Stathio and I played that game as well. And the natural thing to say is that it probably was this steep rising spectrum, but definitely didn't have to be, you know, just really short distance, no correlation at all. But it was, in my view, you know, it was a shell game. It was just being done to play because we know the truth. Well, anyway, I
Yeah,
keep going on. But the main point I'm trying to make is that it isn't so clear to me that your tail is complete.
I think, but it doesn't, the reason I'm not so worried is because the tail always will match on to the
No,
adiabatic.
tail in the TALE sense.
Oh, tail, okay, sorry. I think there will be some deviation, but it won't change. The picture I'm telling you, I can't imagine why, again, the argument, the mathematical argument I'm making, right? If the power, forget about correlations. If the field power spectrum is peaked, I see no way of getting around this fact that the density power spectrum on some scale will become constant. Right? Beyond, at even larger length scales, when you include adiabatic fluctuations, it will again get away from this. Right? But I can't get away from this. I don't know how I get away from this statement.
Well, let me make the general comment, which is we can completely agree with. People have been naive about what is called wave dark matter.
Sure.
And so it required a lot more intense thinking.
Absolutely.
And not many people were doing that thinking, so good for you, and good for you collaborating with Mir Bobby, who's a very good guy. So it's good work.
Yeah.
But we need to know
Sure.
exactly the details.
Absolutely. Sure.
Hi, thanks for a very nice talk. So maybe you have also mentioned this, I was not there. So what is the effect of the baryons, particularly, you know, baryonic feedback, because these are very small scales. So I want to understand it at how confident are you that the extremely small scale physics, like at a scale larger than the de Broglie wavelength scale, will remain because of baryonic effects?
I think I'm less worried about how the baryonic effects will change the dark matter power spectrum. I'm worried about what the effect on the baryons of this will be, right? So, because the observer, to say the obvious, the observables are mostly in the baryons.
That's right.
So that is precisely why we are actually now doing full simulations with baryons included. We have made an estimate of the baryonic gene scale, right? And it still is in the domain that it should see some of this enhancement that's there. On the very short scales, so the game we want to play is we want to make observations as early as possible because the structure is forming early so that the feedback effects where a lot of the uncertainty will be, we don't have to worry about it. But we want to be in the quasi-linear regime where baryonic effects are important, but not so important that that it relies not so much on the bump that is created. To answer your question, I don't have an answer that's clean because we haven't done it on the shortest scales. On the quasi-linear scales, I'm reasonably confident that if this model is what nature decides it is, then there will be implications for how baryons cluster in the early universe as well.
Okay, maybe a more direct question will be, do you think the solitonic core at the high redshift is a smoking gun signature in the presence of baryons?
So is this
Do you think the solitonic core, which you showed in your simulation in the high redshift, is a smoking gun signature even in the presence of baryons?
if you could detect solitons that early?
No,
that would-
I totally agree, but
Yeah,
will it
sure.
stay? If I don't detect them, can I rule out axion? Or can I say that still there is baryon? You don't know. That's what I'm trying to understand.
I see. So I think if you don't find axion stars, that doesn't rule out, unfortunately, axions. Okay, you can't say that, right? Like, just because I can change the mass and this peak can be moved so far into the UV that you will form no solitons at all. Observe. So I don't think, however, if you do detect solitons, I would be very hard-pressed to give you another explanation for how that came about, right? Particle dark matter doesn't have the coherence to form these solitons. If you form them, I would say it is some field that has done it, axion or otherwise. So not detecting them doesn't, unfortunately, rule things out. Detecting them, I think, would be a smoking gun.
Okay, let's thank Mustafa. And the next speaker is Céline Bœhm. And the title of her talk is Dark Matter the Right Concept?
All right, thank you very much. And thank you for the invitation. That's my second time in India, and the first time was 10 years ago, so it feels almost like a new adventure. So thank you very much for inviting me here. And I should say I haven't slept basically for 2 or 3 days because of various combination of things, including the trip. So I'm going to try to do my best for the talk, but it might not be my best talk ever, so I apologize in advance. Now, basically, I thought it would be very interesting to look at whether dark matter is the right concept. This is something I've been working on for a very long time. And even though by trade I'm a particle physicist, I think I start to feel like this is definitely not the right answer. So I like the conference in the sense of rethinking cosmology. I think is probably the right way to go. But I'm actually thinking maybe it shouldn't be just cosmology, but actually particle in the universe, and so more the astroparticle or particle cosmology concept that maybe we need to revisit completely. So the point is, as you all know, obviously, and I should say probably the 2/3 of the talk is not going to be a big surprise to you, but I want to eventually speak about a new concept which I'm very excited about. But so just to arrive to that concept, I want to go through basically all my thinking. And as you know, well, we have 2 theories which are incredible. They work extremely well. We have general relativity. We have quantum field theory. It's all amazing. They're not failing. We have models, and they seem to be pretty good too. But we're obviously trying to see if they fail, because we know that in the end, we don't manage to describe the observation of the universe. So we're missing some ingredients. This is the current status. But maybe actually we don't miss ingredients. Maybe we just miss not the models, but the theory. And so just to go back on this, at the moment, so we're just focusing really on challenging the models. And the models are pretty simple in the sense that what we learn is to explain at least the fluctuation of the CMB, we realize that having just the baryons and the photons, the ordinary matter that we know, is not enough. And we know this because the baryons and the photons couple together, and that's inducing a lot of dissipation. And that dissipation means that you can't even explain the second peak and the third peak of the CMB. So not good enough. And so the solution is very simple. The solution is basically to say, well, why don't we introduce a third a third ingredient, which is basically a collisionless fluid, which doesn't have interaction. So all we need to do is to add a third equation. And that third equation, which we refer to as dark matter, only changes gravity, essentially. So we refer to it as a fluid of particles, particles which do not interact, but neither in that third equation that you see here do you see any sign that it is a particle. There is no mass, there is no interaction, so it could be, in principle, anything. And for this reason, I always think this is actually a modification of gravity. This is a very specific modification of gravity, one which is essentially described by a collisionless fluid, but it doesn't say that it's a particle. Now, you may say, well, actually, we have more indication if we look at the universe as a whole. So we know that basically we see some gravitational lensing. We know that we have rotation curves of galaxy we need to explain, and the expansion. But really what you need in that case is to add some form of mass, which is, again, a modification of gravity. And what you really want to avoid is a form of dissipation. So we're fighting dissipation, and somehow we want some mass. And of course, we want some form of acceleration. But again, it doesn't tell you that you need a specific particle. So even though I say that, for a long time, obviously, everybody has been hunting for particles, and everybody has been looking for particles which do interact very lightly and weakly. But the point is, 20 years ago, this was really exciting because we didn't have any constraints. But now we arrive to a point where the constraints are extremely, 40 years ago even. But I think until 20 years ago, I think it was still fairly exciting. But now it's starting to be really complicated. And so all the green region here on this plot is basically excluded. And this is basically the progress that have been made in 20 years. People have gained, dark matter direct detection experiments have gained about 20 orders of magnitude in the space of 20 years. It's remarkable in terms of experimental progress. Now we arrive to a point where you can see the pinkish region, which is the neutrinos. This is where the dark matter direct detection experiments are going to detect neutrinos. And what you see is that dark matter now has to be interacting almost like a neutrino, or even less than a neutrino. So it's even more elusive than a neutrino. Who expected that? Maybe a few people, but not so many in the community. Now, you can see, so the plot on the left is 2021, the plot on the right is 2024, and again, the experiments have gained several orders of magnitude in sensitivity. So it's actually going faster and faster, and now we're touching the neutrino region, which means that those experiments are detecting neutrinos now, or are about to. And just the new result here, just to compare, sorry, I'm not sure. Yeah. Now you can see that they're really hitting, and they're starting to probe the neutrino region. So remarkable achievement for those experiments, remarkable achievement in terms of trying to understand what dark matter is, but what it's telling us is that it's not what we thought it was. And maybe it's still basically a particle, heavy particle interacting very weakly, but clearly the interaction have to be so weak now that we're going to have difficulties to probe this model. If you were really attached to thermal dark matter, there's been a lot of changes too because of Planck. So 20 years ago, we could also play with a very large parameter space. So on the left, this is an example with supersymmetry. The two panels are supersymmetry. They're actually not the same parameters, so it is an important remark. But you basically could do, 20 years ago, you were dealing with a parameter space, which is like the green on the left, which was fairly large. Now, it's the line, the vertical line on the right. This is basically extremely reduced, and then if you add the constraint from direct detection, you see that it's almost all gone. So this doesn't mean that supersymmetry is ruled out. It doesn't mean that dark matter is ruled out, or heavy dark matter is ruled out, but it does mean that actually it's very hard now to have models which you can probe, basically, in any particle physics experiment. Now, there are always hopes, and recently there's a law, there is a paper which made a lot of media interest, or rich media interest, about possible gamma ray signature in the galactic center. It's very close to the gamma ray waves, the gamma ray excess from the Fermi data in the galactic center. But actually, when you look at the cross-section, they completely exploded. So I'm not sure how one can make this claim anymore. So maybe there are some tricks I didn't realize, but it seems to me like even that will not make it. The reason is that we have constraints from absolutely all the channels. So not only do we have direct detection constraints, but we also have constraints from indirect detection, which is looking at the cosmic rays basically produced by dark matter, which propagate and arrive to us. Now, the region which is still okay is when dark matter doesn't have interaction with us. And there is a specific scenario, for example, in supersymmetry with so-called particle called xenon, where this might be the case. But again, it seems like at this stage, to me, it seems extremely unlikely and not what we expected at all. So if you're not convinced that dark matter is a heavy thermal candidate, for example, or a heavy particle, then what do you do? And you may want to stick to the dark matter particle concept. And by doing this, then you can say, well, okay, I relax all constraints. And the question is, can you do that? And this is an observation I did when I was actually a PhD student, so it's quite a long time ago. But I realized that we were only probing, we were only making assumptions on a very tiny part of the parameter space for dark matter. And in reality, what you have is you should be very agnostic, and you should consider all possible mass, as we heard this morning, and also all possible interaction type. When you do this, you can actually classify, using the free streaming of dark matter, you can actually classify the type of candidate you expect. And there are not so many, so you can compute basically the free streaming for only 6 regions. It's tiny, it's a little bit more complicated than that, but basically there are 6 relevant regions where you can do this calculation, you can order them, and basically you can check whether dark matter is the candidate you have in one of these regions is a possibility or not. But when you do this work, you realize that, well, you have interactions, you can't really neglect them, or that's a question, I guess. So if you have dark matter, even if it's relatively heavy with interaction, what is the effect? For example, on structure formation, does it have an effect? Because so far, everybody has, at the time at least, has assumed that dark matter didn't have any interaction. And you use the collisionless fluid approximation to understand structure formation and to predict the CMB. So what happened now when you actually try to be a little bit more realistic? And, sorry. Yeah.
So you don't have a scale on there.
Yeah.
Is gamma an order H at the decoupling, or is gamma related to MDM?
Yeah, so gamma can be anything.
I realize that, but
yep.
Let me put it this way. I'm quite enamored by treating gamma as a dynamical variable, which I think it is.
Yep.
And so it is quite possible that, the M resonance is just not stable,
yep.
and it decays away,
yep.
and that would then say it would be interesting to plot gamma over MDM. But cosmologically speaking, it's usually gamma over H at the time of decoupling.
Yeah, correct. So, so for example, you have a line here. So maybe, so here this line corresponds to the moment where dark matter is basically becoming non-relativistic, but also equal to the equality. And then, yeah, so the decoupling would be here. So anything here above here we consider as strongly interacting, and below is more weakly interacting. But I think if you want to have a proper description, I'm going to show it. I think hopefully I'll answer your question.
Sorry, I'm interested.
Yeah, no, I I do agree. I think it's an important. Yes, thank you. So yeah, so in principle you can do it generically and looking at the free streaming, but then as you have interaction, you should also look at the collisional damping. And you can do this at the time, I mean, a long time ago I was doing it in a very holistic way, but very simple way. Now you can do it, I think, more professionally with Boltzmann class. A lot of people, many people have done this kind of exercise, and many people have done all sorts of coupling. So I just want to take one or two examples, which I know the best. So for example, you can couple dark matter to photons. Now everybody would say, well, no, you can't, because dark matter is invisible, doesn't emit visible light and so on. But the question is, can you actually do that? Is it allowed by the data? To which extent you can have a dark matter photon coupling? And the answer is you can, and the cross-section can actually be very large, and still you won't see it in the data. And that, to me, is mind-blowing, because we all assume dark matter is neutral, but actually the simple exercise of coupling dark matter to photons basically can modify the CMB, but not depending on the cross-section and depending on the mass, you may never see it. So it can still have relatively large cross-section. In this case, for example, for a particle of 1 GeV, the cross-section is almost 10 to minus 30 centimeters square. There is no way you'd assume that this is possible, and yet this would be allowed by those data. Now you can look at the power spectrum, and what is very interesting, and it's a feature which is true for any kind of dark matter interactions, is you induce dissipation. And you induce it in a way which is essentially the Bessel function, so it's exactly like having baryons photon interaction, except now you have it in the dark matter sector. So why is it interesting? It's because you actually, depending on the value of a cross-section, you may actually fit the very large scale structure, but then you have effect at very small scales. And that is interesting because you have this dissipation, but you don't have it at a very large scale. And so you may mimic scenarios like Bœhm dark matter to scenarios with dark matter interactions. So there is one particular scenario I really like, which is the dark matter neutrino interactions, for the following reason. So you modify the CMB, but you can actually play with the cosmological parameters to make it similar to lambda CDM. And if you do that, you end up with a scenario where dark matter can have weak interaction with neutrinos, and yet you can have huge effect in structure formation. So I'll show you them after. But I'd like you to pay attention to this cross-section. It's actually fairly weak. If you have a particle of 1 MeV, for example, it would be this value. If it's lighter, then it's basically like the weak interactions. Now, if you do that, at the time at least, we found that this would actually imply that in order to make the data, I mean, to make your prediction compatible with the data, you need a very large value of H0. And so this was actually a model which was very interesting, at least at the time, because it says, okay, maybe actually this is a solution to the H0 problem. Now, when you take into account the Planck data, the latest Planck data, then it's actually, this value is too high, and then you're basically back to the 67 kilometer.
What does it change H0? That's set by the first people.
Yeah, so
It's not modified by this.
no, so you have the first peak, but actually you have a tilt. So here I show you just this value. You basically have already, you have NF, H0, and a few other parameters. And then you, yeah.
Spectral field is also going towards 0.99.
Yeah.
So, and when you see that you try to force it to 67, it goes back again, right?
When you really use the latest polarization data, essentially, it brings you back to the normal LCDM. If you don't add them, then you actually, you live happily with those values.
Do you see anything with when you change not just the polarization, large L polarization data? If you use something like CMOL at the low L part, low LTEE, your tau is going to go down.
Yeah.
Does it have any effect? Do not use the
high scale.
Yeah.
Yeah, we didn't do that exercise, so I'm not sure.
Okay.
It's possible that I think the polarization data are the most constraining. I would need to
Okay.
check though, doing the exact exercise.
Because it
but-
seems that here everything is changing. Tau is also changing,
Yeah.
NS is
Yeah,
also
yeah.
changing. So
Exactly.
which one is responsible? So if you bifurcate them, then that
I
would have been
believe
informative.
it's NF and S not, but I
Okay.
would have to check. But
Thank you.
But the interesting point is that now we have a scenario where you have a weak interacting particle, which is relatively light, but not that light, which is actually changing the CMB, even though the interaction is very weak. So you would not guess that. And the other thing which is very interesting is that it does change, it's not in principle. And again, when you put the constraints, probably not, but I think from a theoretical point of view, you end up in a situation which you didn't expect naively, and I think that calls for being careful and looking at all those scenarios in more depth. Now, a lot of people have worked on this, and so some people have, some people have made some refinements. That particular model, for example, rely on specific diagrams which I'll show in a second, but you can have a resonance, and those people have taken into account the resonance, which I've never done. I have pointed out the resonance, but never did the exercise. And they also realized that with the evolution between the mass of a neutrino and the evolution of redshift, you have a very interesting effect. So there's a lot of phenomenology here, which we're actually looking at the moment. I don't think those scenarios are excluded, but they're very interesting. But it's only interesting.
Just curious about because post-Planck there's also ACT and SPHEREx
Yeah.
revolutions,
Yeah.
which are much more constraining
In the polarization. Yeah.
So what's the take on that?
So we did the exercise a few years ago with preliminary data. I guess now we would need to do with a new.
I think it's going up pretty high.
Yeah, and that's really I think that's really exciting. Yeah, I suspect this is going to constrain the scenario further. But what is not clear to me is what happens when you really do the proper modelization, which I never did actually. So I only consider. So I had the resonance, for example, in those models, but I always consider that I was on one side of it, and those people are doing just the evolution, properly. That's
As far as I remember, that ACT collaboration has performed a modified non-lambda CDM paper as well. I'm not sure about this particular reaction, but there are
Yeah. But so the point is, for me, is not so much the model itself. I would doubt this is a correct description of nature, but really the call for let's be agnostic and let's not assume the dark matter doesn't have interaction. It's a collisionist fluid. For me, all those are examples of let's be very careful about what we make, like the kind of assumption we're making. And one thing was you have more effect when the dark matter particle is light. And again, the question was, well, can we have light dark matter? And can we have light thermal dark matter even? And obviously today, I would say probably the answer is no. But at the time, the whole point was, well, if you use this equation, everybody was using this, and everybody assumed that the cross-section, was scaling as the dark matter mass squared divided by the mass of the mediator to the 4. And there was one assumption nobody really spelled out at the time, which was, well, if you have a charge mediator, then because it's charged and you impose a specific value for sigma v, you're going to actually have a heavy dark matter candidate. And so because of that, everybody was convinced you could only do heavy dark matter. But if you take a different cross-section, and all it needs is a different mediator. So if you find, for example, a mediator which is either light, and so this means probably neutral, or a particle or a different type of interaction, then you can essentially have a cross-section which is no longer dependent on the dark matter mass. And from that moment, then you relax all the constraints. So those are specific examples. I see that I'm running late and I really want to reach my third part. So I'm just going to pass very quickly, but those are basically realizations where you could have like dark matter. Now again, 20 years ago, we didn't have much constraint. Now we have all those constraints. Again, an incredible achievement from the experimental point of view. And I'd say now the scenarios that I liked, they're starting also to be constrained now by IceCube even. So we're really in different area. And for that reason, I think we really need to think carefully about the particles in the universe as also on top of the cosmology itself. Now, the good thing is, just a parenthesis, the good thing about all those experiments and not finding the dark matter is that you can suddenly you validate the standard model, but at incredible low energy. So those experiments on top of probing neutrinos are also very good at probing the standard model. And I wanted to make a point about, if you look at the power spectrum, you may have signature at large redshift, but as you progress toward today, you look like lambda CDM, which for me means it's not because you see lambda CDM that you actually have lambda CDM. It may be that actually your cosmology is much more complicated. Those are possible signature. I'll pass. And maybe I'll just highlight this. This is, I think, controversial, but we did this exercise where we had dark matter interactions. And having dark matter interaction, we found that actually there could be a change in the number of binary black holes you form, and this would have actually a change in the rate of gravitational waves. And with redshift, we believe you could potentially probe this. I think that's controversial in some ways, but I do think this is a very interesting exercise, and it would probably deserve to be redone by experts of the field. All right, so the rest is probably, you've seen many times, so I can go fast, but if it's not a particle, then it could be a wave. There are many constraints again, and that we've seen this morning, for example, that you have some simulation, and I think the message is the same, that you have lots of constraints, not clear to me whether this is the dark matter candidate, but the large-scale structure and the formation of galaxies are going to be a good space for constraining those scenarios. Now, if it's not a particle, then it could be, for example, prime-order black holes. Again, lots of constraints. You need different mass to make it work. I'm not convinced, but it could still be a possibility, I guess. And then you could say, well, actually, if it's not a particle, a wave, a prime-order black holes, maybe it's just a modification of gravity. And, well, a while ago, the best we had was a relativistic version of MOND, which was called TVES, but TVES couldn't explain the CMB. And recent developments for me was quite really groundbreaking in the sense that now you had this incredibly complicated theory by Scordis et al. But that theory basically had in the action a mass term, an effective mass term, and that does reproduce dark matter. And as a result of that, and you have two regimes. You have one where it's basically Newtonian, the other one is like MOND. So basically, in the early universe, you behave like a normal FRW and LCDM model. And then in the galaxy, you start to have basically modification of gravity. So those models, for me, were groundbreaking in the sense I think it's the first modification of gravity which does reproduce the CMB. And that is, for me, a change in the paradigm, because suddenly we can't just say dark matter has to be a particle. Now you could say, well, actually, it could be a modification of gravity. There are signatures. I don't think that's the right theory for the following reason. When you look inside a galaxy and how basically gravity behaves, you start to see that you have a Newtonian regime, then you have a MOND regime like you expect, but then you start to have an oscillatory regime where basically gravity can be positive or negative. So that is probably unrealistic. But this is the first realization of a modification of gravity that does fit the CMB, and I think this is absolutely massive in terms of implication for dark matter particle. So this is my last point, and probably don't have so much time to explain it, and it's very complex, so I'll try my best. But for me, when you say, well, when you look at all the constraints for dark matter and all the other, like dark matter particles, dark matter alternatives, for me, there is a point of where you say, well, we don't find it, maybe it's time to rethink cosmology. And maybe it's time to rethink the concept of gravity. Now, how do you do that? Well, first of all, maybe we need to look at different scales and all the scales. And there is work by Job Feldbruch, which I think is incredibly powerful. It's been 10 years in the making, so Job has done a lot of maths, and I think absolutely remarkable. And to me, it's going to lead to groundbreaking results, and I hope I can show you now. Maybe I'll pass quickly on the theory, but just to tell you, well, the main thing is you want to look at the displacement field here. And we know that as you form structures, you're going to have some folding. As you do the folding, you're going to have shear crossing, and that generates acoustics. Now, that acoustics, that's not a new concept. This was actually introduced by Arnold and collaborators a long time ago now. And the concept in some ways was simple. You have a relationship between the displacement field and the gravitational potential with the growing modes. And then you can express this in terms of eigenvalues. Now, the relationship between this and the density is that basically the eigenvalues enter into the denominator here. So you can see that if mu is equal to -1, then your density explodes, and that's basically your acoustics. So you can do it in 1D, you can do it in 2D, but then after that, basically they stopped because they couldn't find the way to generalize it to a higher dimension. And Job's work has been to do that work, to generalize it to higher dimension. So I think if Arnold couldn't do it, it tells you how much Job's work has been impressive. At least I am very impressed. And so what he has done is basically the breakthrough was to embed the work into a manifold. There's a lot of math which I'll pass, but basically he has found a way to generalize the definition of the eigenvalues, and then basically that still goes into your density field. So that's the math, and you can read the papers. But essentially what he found is that you have an iterative process. So you start with the folding, which is your A2 acoustics, and then you continue iteratively. You end up with a A3, which is like a wall. And that's a cusp, and then A4, and so on. And so in practice, what it means, so if you see the, I know I'm late, but I'll go fast. If you basically take space-time as a sheet, then you're basically folding it. And what you get in 2D, you have your first folding, the shear crossing. And then eventually what you see is that you have different acoustics, but you have one filament and two clusters, A4 and D4. That's 2D. And when you generalize it to 3D, then you start to have two clusters as before, but you also have now two types of filaments, A4 and D4. And what it means concretely is that when you start your initial condition, you find your eigenvalues, you evolve. At 2D, so you find your A2, your A3, and A4 and D4. But when you do it at 3D, you start to find walls. So this was done by a student of Job called Bœhm. And basically now you have a simulation at 3D of a universe, and you can find not only the filaments, but also the walls. So it's basically the separation between the different regions. And that never has been done before. People are using dispersed code, for example, that's not doing the same work. Now you can apply it to the local universe, and that's been done by my student, Amélie. And that is basically the stickman. And we think, the stickman as a 2D structure in space. Well, actually, now we can do it in 3D. We can see the folding. And now we can identify galaxy in that 3D structure. And we realize that some galaxies in the stickman do not belong to the same type of filaments. And so those results will come in 2026, sorry. But just to stress, so if you, for example, you can now find galaxies and you can identify where they come from, what was the folding of space-time which actually led to that incredible structure. So I do think it's a new understanding, a new interpretation also how the universe come to be. All right, so it was a bit of a rush, but I hope I convinced you that first of all, based on the CMB, dark matter, if it's a particle, doesn't have to be a collisionless. Can have collisions. It doesn't have to be heavy, and that we know that, but it could actually be even some MEV type of dark matter, and that would actually work. There are more and more constraints, but the real probe, I think, is the large-scale structure. And then I think where we're coming now with putting all the constraints together is we do need to understand gravity better, and we need to study, for that I think we need to study the large-scale structure and their formation. And I think there may be some hidden geometrical structure that we need to explore, and I'm hoping that this will lead us to a new evolution. Thank you.
It's very nice to see Job's work being applied to data. Looking forward to the work. So I have a different question. So my understanding of small-scale effects in dark matter was always that you could try to evade the CMB, but then things would show up in large-scale structure because in the halo mass function,
Yeah,
or in
correct.
the stuff that Orko and Shadab and I were doing with small-scale statistics. So can you comment on how your weakly interacting modifications play, for example, with the Lyman alpha forest or with late time structure?
Yeah, absolutely. Sorry, I have to go back to somewhere late. Yeah, so for example here, so as I said, you're going to somehow go back to a form of LCDM, but you're absolutely right. When you look at the mass distribution, then you see differences. If it's too extreme, you'll see also it in the filaments. But mostly what we're expecting is the cross-section is too small to have a very large impact on large scales. And you would see it when you look at a structure like the Milky Way. And so essentially it's close, depending on the cross-section, and that's your constraint, you're going to be looking like warm dark matter. So in terms, for example, the Milky Way, you'll have many less satellite companions.
But you will evade Lyman alpha forest constraints?
So we basically make sure that we do. So this means that this turns into a constraint on the cross-section.
You made a reference to disperse and some comparison. Can you please elaborate on that?
Yeah, so disperse is basically looking at the filament structure using Morse theory, but it's mostly doing it in 2D in some ways. So you can't really reconstruct the walls. It doesn't really help you to reconstruct the whole structure that we see here. So you can't really apply it to really understand, for example, like the stickman. We're going to see it like fold with time. Disperse cannot help you to do this. You're not going to determine the different filaments, the different acoustics which are playing here.
So just to follow up on that, these things like the flip-flop field and so on that Sergei Shenderin and people worked on, and then Tom and people have worked on this folding of. How is this different? I couldn't quite follow.
It's the same, except that it's what Job has achieved is the generalization of that work in 3D. They stop at 2D.
Well, he did classification in 3D.
Okay, classification is different. Okay.
Singularity.
Yeah, and so then based on that, you can now analyze the simulation in 3D with the new formalism.
Yeah, except it wasn't clear for me why are you talking about folding of a space-time?
Oh, yeah, maybe I shouldn't. This is my interpretation. I see it as you start, so all in this theory, you're just doing Zeldovich approximation.
Yeah, so you kind of fold a cold sheet in a phase space.
Yes, and to me, I think there is much more value than just saying it's dark matter. In principle, it's just a dark matter sheet. To me, there is much more value to that, but I can't show it. So yeah, you're right, I shouldn't.
Could I just make a quick comment? So it doesn't work in 2D either. What happens is that the folding is such that it's so vigorous that you don't remember that Lagrangian sheet. So it's a multi-dimensional thing that's hierarchical in scale, and what it leads to, not surprisingly, is that you get a temporary equilibrium that are called halos. They would be called equivalent things in 2D. And you can't describe that by Arnold, Shindar, and Zeldovich. And that was recognized very early. And no matter what you think you can do with the generalization, it is not going to describe the heart of the halo.
Well,
but what I do agree with is that you can actually describe everything, if you like, in terms of geometrical complexity associated with folding. But you can't really say, oh, I've seen this caustic and all of that. These are going to have been specialized ways of looking at the data, but it's not going into the full multi-dimensional aspect of what actually happens under gravity.
I'm not sure I agree, because we do have, now we have, so we use the
you've just got labels, but the one thing that you won't get from this is you won't get the masses. You don't get the masses by these geometrical methods.
We have velocity fields and we have a density fields. So I think we can have a mass.
Well, this has been a problem with adhesion and all of that over the years. It has the basic geometrical structures but it doesn't have the concentration points that are concentrated enough, so it can't get the masses.
I think I disagree, but I guess that this is the part of the work, so we'll be able to tell you if you're right or not.
Now that dark matter is light, where are the light mediators? Why have you not seen them at accelerators?
Well, because the coupling is very small. So obviously, when I was doing it, there was no constraints, so that was easy. Now, obviously, there are lots of constraints, but there's still a room. Small is the same as for the axons.
But you would see them through radiative corrections, even if you don't produce them on shell.
No, because the coupling is small, so you don't have
Just
a.
dial both down
Yeah.
to keep the ratio the same.
Yeah.
So this is
Yeah, exactly,
this
exactly.
is the limpless argument.
Yeah, which we were doing at the time. Yeah.
Hi, thanks for the very nice talk. So a couple of questions, but I may have to stick to only a few of them. So here, Céline. Here, over here.
Oh, sorry.
Yeah, so I'm really curious about the relativistic MOND.
Yeah.
So it's given number of degrees of freedom, I can match with CMB and large scale structure. But now, what I'm curious to understand is that where the transition happens. Where the transition happens from Newtonian to MOND, and what is the observable effect? Because we can, in principle, make tomographic estimates of power spectrum from large scale structure.
Yeah.
And how deep we need to go to falsify it?
Yeah. So look, I don't think this theory is going to be the theory. So, but as I said, it has a merit to reproduce a CMB, and that in itself, I think, is a huge achievement. Now, so you have this parameter, which is like an effective mass, but that's basically fixing the, I mean, it's a very complicated theory, but it's basically fixing the transition. And so on this, on this one, no, to be honest, I've forgotten exactly the formula, but it's basically that regime where you start to have a departure from Newtonian, where you start to enter MOND. So it's between the green, your potential, your MOND potential is in green, and then Newton is in blue, and you start to have this phase here, and then for this, to be honest, I should have checked, but it depends on the dynamic of those fields, and then we found that basically at some stage you enter the MOND regime, so I've forgotten how we define it exactly, but I can tell you, I need to look at the paper again. But you have this transition here. But then after that, here, you start to depart again from MOND, and then you enter this. This is basically your real, I should have said here, is your real description, is your field, the gravity field. So here it stick to this, then it start to be like sticking to MOND, but then start to be oscillatory. When you go here, you basically go to a different regime. That regime, so you can push it with this parameter mu, so you can make sure that actually it doesn't happen in the galaxy. It could be outside the galaxy. But then this means that near the galaxy, you have gravity, which is attractive and repulsive. So I don't think, that's why I say I don't think this is going to be the theory.
Okay, so because there may be a redshift information we can use and already rule it out at high
Yeah,
redshift.
I think anyway, this is just going to be excluded from.
That's right, yeah.
It's a toy model, but if you look at, it's a toy model which is, hard. Yeah, it's super interesting, but very hard, you know. So the thing is, when you look at the price, for me, the thing which is really important in the concept, I mean, in the context of thinking about new concept of cosmology, is the level of complexity to reproduce the CMB. And at the end, you still need to have this effective mass. Yeah. Yeah, so you have several fields. I have a slide somewhere, but yeah, you have many fields, and they need to turn on for, yeah.
So there's, I mean, very nice talk, but if you just do a dichotomy, right, people have also talked about an option 7, where modified gravity, instead of dispensing with dark matter, can act as a source of dark matter. Yeah. So 2 or 3 efforts I know of is, I think, Postnov has written papers on massive graviton dark matter. Yeah. Slava Mukhanov wrote a paper on mimetic gravity, where you have an integration constant after you do some conformal transformation. Yeah. Dan Hooper has written papers on Kaluza-Klein dark matter. There are probably others which I don't know. So what is your opinion on this? Is nobody has discussed or will discuss this option, I thought. Yeah. So what are your opinions?
Thanks for pointing out. I guess, you know, at some stage I was limited in time, so you're right. There could be, and I think to some extent the work Job is doing, to me, seems like as I said, there is a deeper interpretation. I don't think I should be speaking about what I think it should be, but it could be related to emergent gravity. So I wouldn't be surprised if we have to revisit the concept, not just of dark matter itself, but actually of gravity, where it stems from, and perhaps space-time. But I'm really speculating. I don't have any means to justify what I'm saying. So.
You just said you didn't want to speculate on it, and I was just interested to hear more of your thoughts on your last sentence on your slide. You said that this work might reveal the hidden geometry of the universe. What do you mean by that? Is that in the context of other modified gravity theories that might have similar caustics and then similar observables?
I think more in terms of, and I'm relating things which I don't really want to speak because I feel like I'm putting things together, which and I'm not going to show you anyway. So, but there are structures we see from the work that the students are doing. We already see things happening with the walls and the filaments. We can see, for example, that so all the walls, and it's normal to expect that, but all the filaments are on the walls. And then in the filaments, you have deeper structure, you have other filaments and so on. Now, all the galaxies would be on those walls and the filaments. And when you look at, because there are different type of filaments, when you look at the structure, I think it's starting to say that the formation history of those objects is different. And maybe this is not true, but from this work, it seems like you have basically a different type of formation. And that led me to speculate, I guess, that maybe there is, if it's really a folding, why would be this particular folding? So this makes me think and based on other work I've done, that there is an internal structure, and we're not following just a random folding in some ways, that there is a driving force. And that driving force here is essentially gravity, but it could be actually a more subtle concept, basically a different type of notion of gravity. But as I said, I'm really speculating. There's a lot of things I'm thinking from different work, which I'm not showing here, and I don't really want to show, but I do think my intuition is this is fundamental work, and we need to pay attention. I might be wrong, but I really think I'm personally like 100% on it now, and I should be also to look, because I think there is something there, and as you know, maybe it's not true, maybe it's not going to produce the real illusion.
Okay, so we are running very late, so let's thank Céline, and we'll keep discussing about 2:30.
Demotivated me to look at jobs, the papers, which I'm still trying to understand because they're very dense. But
very much.
Two of the remarks you made.